In this video, we're going to be connecting rates of change to something called a derivative. Now, Calculus 1 is often referred to as differential calculus, and the word differential is essentially coming from the word derivative, which is a very major topic in Calculus 1. So recall from an earlier section that if we have some fixed point P with the coordinates a comma f of a, and some variable point q with the coordinates x comma f of x, and these are two distinct points on the graph of some function f of x, then the slope of the secant line that passes through p and q is given by the formula f of x minus f of a all over x minus a. So let's look at these graphs that we have here, and in this first graph I'm going to call this point here a, and then the y-coordinate of that ordered pair would then be f of a, because this is a graph of the function f of x, and then this point here I'm going to call that x, and the y-coordinate of that point would then be f of x. So again, from this picture, I have this secant line here. So this here is our secant line. And if I wanted to come up with the formula, I could copy that down again just from what we had above. So the slope of the secant line is f of x minus f of a over x minus a. And remember, this essentially comes from the slope formula y2 minus y1 over x2 minus x1 when we're thinking about these two ordered pairs p and q here. Now, I'd like to do this same thing, except we're going to define our order pairs for p and q slightly differently. Well, p is going to stay the same, so the x-coordinate for p will be a, and then the y-coordinate will still be f of a, because we still have our function f of x here. But now I'd like to define my other ordered pair slightly differently. So the way that I want to define this is, suppose that I would like the distance, the horizontal distance between my two ordered pairs p and q to be h units, where h is just some arbitrary number or arbitrary distance. And so if I'm starting at a and I need to travel a distance of h units, then this next x-coordinate must be a plus h. And remember here, this is the point q, and then if I am thinking about the y-coordinate of that ordered pair, then that would need to be f of a plus h. So let's come up with a formula for the slope of the secant line in this second image as well. So we have the slope of the secant line is equal to y2, which in this case would be f of a plus h, minus f of a, so that's y1, over, now I need to subtract the x-coordinates. x2 would be a plus h, and then x1 would be a. Now, I can actually simplify this expression. Notice my denominator can be simplified to just h, because a and negative a will sum to 0. And then my numerator, I'd have f of a plus h minus f of a. So now I have these simplified formulas for the slopes of the secant lines in both of these graphics. Now I have this similar image here, and I still have this point P here, and I have Q here. And remember, P is fixed and Q is variable. And historically, before this section, what we've done is we'd like to approximate the slope of the tangent line at some point on the graph of our function. So in this image, our goal is to figure out what is the slope of the tangent line at p for our function f of x. And the way that we've done this before this section is we've calculated the slopes of secant lines. So what I'm going to do is I'm going to take my point P and my point Q, and I'm going to create a secant line by connecting those 2 points. And then again, what we've done previously is we've chosen our Q point or Q ordered pair to move closer and closer and closer to P. So here's another instance where I'll draw it and then I'll form that secant line. And so now I have another instance of Q here. And then I'm having Q travel even closer with this next secant line. And I have this next secant line. And then I have this next secant line. And we keep making Q and Q closer and closer to P until eventually it's very close. So maybe now my Q is here and I've connected these with a secant line, and we're just having that kind of be an approximation for the slope of our tangent line. Now, there's two ways that we can find the exact value of the slope of the tangent line, and by having Q move closer and closer to P, in this second drawing here, what we are doing is we're having H, which represents the distance between the two ordered pairs P and Q, get smaller and smaller and smaller. So how does that tie into what we've been learning so far in this class? Well, in other words, H is approaching 0. And we can define the slope of our tangent line to be the limit as h approaches 0 of the slope of our secant line, which I'm just going to copy down here, f of a plus h minus f of a all over h. And something that I would like to point out is this thing right here. This should seem familiar if you've taken pre-calculus. In pre-calculus, you learned that this thing is called the difference quotient. And so now you can see why it plays such an important part in Calculus 1. So this thing is called the difference quotient. And previously, we've also learned that the slope of the secant line, we've referred to that as the average rate of change. And if we're talking about position and movement, we can also think about it as the average velocity. And then the slope of the tangent line is now the instantaneous rate of change. And again, if we're talking about movement of like a particle or a car or something like that, or an object, we can also think about it as the instantaneous velocity. So now what I'd like to do is I'd like to come up with another formula in the first picture that we drew. So in this case, we'd have that the slope of the tangent line is equal to the limit as x approaches a. So here in this first picture, our x coordinate here is moving closer and closer to a. And so we have the limit as x approaches a, again, of f of x minus f of a over x minus a, which this function is supposed to represent the slope of the secant line. So we have two different definitions now for the slope of our tangent line. One of them is this thing here, and then our other one is this thing here. In this section, we want to explore how we transition from secant lines to tangent lines. Notice from the visuals above, the way that we go from a secant line to a tangent line is by having one of these two situations. We either have x approach a, which that's what we have here, or we have h approach 0, which is the scenario that we have there, depending on how we are thinking about the ways the ordered pairs are moving closer together. As the ordered pairs get closer and closer together, the average rate of change, or the slope of the secant line, is approaching the instantaneous rate of change, or the slope of the tangent line. So let's formalize this definition. The slope of the tangent line to the curve y equals f of x at a point P, which has the coordinates a, comma, f of a, is given by one of the following two definitions. So these are both the formulas that we saw above. And I just want to emphasize, it's very common to see both of these formulas, but moving forward, if you're in my class or if you're going to continue to watch my lecture videos, I'm going to focus on this second definition here. So typically, if you see me doing computations or calculations, I will be focusing on this second definition, but I'd like you to be familiar with both of these formulas. So both of these give us the instantaneous rate of change at a specific x value, which we are calling a. A could be any number like 2 or -7, and that is where we are finding the instantaneous rate of change, or the slope of the tangent line. So let's go ahead and look at an example. So in this purple box here, we have some review from algebra. These are the three forms of a linear function or a line. We have slope-intercept form, point-slope form, and standard form. Example 1 says, consider the function f of x equals 1/4 x squared plus 1 with a domain from 0 to 4. Use this info to answer the questions below. I just would like to highlight that this thing here is a quadratic function. A quadratic function is an example or a special case of a polynomial, and polynomials always have a domain of all real numbers unless we restrict the domain, which we are restricting the domain in this instance to be 0 to 4. So part A says sketch a graph of this function. This is a quadratic function, so its graph will be a parabola, and its vertex is going to be at 0, 1. If I were to evaluate f of, let's do 2. F of 2 equals 1/4 times 2 squared plus 1. That's going to be 1/4 times 4 plus 1, which will simplify to be 2. So my graph is going to go through the ordered pair 2, 2. I'm going to also figure out what is f of 4. That's 1/4 times 4 quantity squared plus 1. 4 squared is 16. And 16 divided by 4 is 4. 4 plus 1 is 5. So my graph will also go through the point, 1, 2, 3, 4, 5, which is here. I realized I drew that ordered pair too high. My apologies. So 2, 2 is here. And it's going to form basically half of a parabola that's going to stop at 4, 5. So let's see. This is 4, 5, and then this here is 2, 2, and our y-intercept is 0, 1. So that's it for part A. Part B says find the slope of the secant line that goes to the ordered pairs 2, f of 2 and 4, f of 4. Oh, look, I already solved for f of 2 and f of 4. That's convenient. So now what I'm going to do is I'm going to connect these with a straight line, and our goal is to find the slope of that line, and there's a couple ways that we could do it. I'm going to start off by using the slope formula. So this is for part B. We have the slope of the secant line is equal to, I can label these, I'll label this x2, y2, x1, y1. So I have 5 minus 2 over 4 minus 2, and that is 3 over 2. So there is the slope of our secant line. Now part C says, give the equation, before I move on to part C, I just wanted to also highlight that we could have found the slope visually by starting at this point, going up 1, 2, 3, and then, so we're going up 3 units and then right 2 units. So using the idea of rise over run, we could have gotten the same fraction for our slope. Okay, so now part C says give the equation of the secant line that goes through the points P and Q defined in the previous part. State your answer in point slope form and in slope intercept form. So this is part C. I'm going to start off with point slope form. And from above, we can see that point slope form is y minus y1 equals m times x minus x1. So I just need an ordered pair that is on my graph and the slope. And for point slope form, it's nice because you can use any ordered pair that falls on the graph of your function. So I'm going to use the point 2, 2. That's right here. So I'm going to fill in y minus 2 equals my slope, which we calculated in part B, and then we have x minus 2 in our parentheses. So when the question asks for the equation of our secant line in point slope form, this is our final answer. Part C also wants us to give the equation of this line in slope-intercept form. So the way that I would do that is I would isolate y, but before that I'm going to distribute 3/2 into my parentheses. That would give us y minus 2 is equal to 3/2 x minus 3. And then from here I'd like to add 2 to both sides. And then we get y equals 3/2 x minus 1. So here is the equation of our line in slope-intercept form. Part D says find the instantaneous rate of change of f at x equals 2. So now what I want to do is I'm going to draw my tangent line here, and our goal is to find the slope of the tangent line, because remember, the instantaneous rate of change is the same thing, or we can find it by finding the slope of the tangent line. So here's our tangent line here at x equals 2, and by finding the slope of our tangent line, we would find the instantaneous rate of change. Now on the previous page, we came up with 2 definitions to find that. And I'm going to reiterate, I'm going to use the second definition. So the limit as h approaches 0 of, and normally in our definition we have f of a plus h minus f of a all over h. Now in this case, our a value is our point of interest, or our x value rather, and so that is 2. So I'm going to go ahead and replace a with 2 in both of those instances. Now, I was teaching a lesson earlier this morning, and I really want to emphasize this based on something one of my students said earlier today, and I want to highlight that this thing here, f, is not a variable. It represents a function, and so hopefully it is clear that you do not want to distribute f and multiply to these terms, because again, f parentheses 2 plus h is not a notation for multiplication. It is a notation for function values. And so I'm not multiplying. What I'm doing is I'm taking 2 plus h and I'm plugging it into the function and then seeing what that equals. And then we're going to subtract off f of 2. And we've already actually evaluated f of 2 here. So here is f of 2, and we found that that was 2. All right, so we have the slope of our tangent line is equal to the limit as h approaches 0 of, let's remind ourselves, our original function f of x was equal to 1/4 x squared plus 1. And so I'm going to take 2 plus h and plug that into my function. If I do that, then that would give me 1/4 times 2 plus h quantity squared plus 1. And then we're going to subtract off f of 2, which again, from the green highlight above, we can see that that is 2. So once again, f of 2 is equal to 2, and then f of 2 plus h is equal to 1/4 2 plus h quantity squared plus 1, and then we can't forget the h in the denominator. Okay, so If we're thinking about how to compute this limit, since we're taking the slope of the tangent line and we can see it visually, our final answer should just come out to a number since we're measuring the slope. And if we're trying to simplify this limit, one thing we could try is direct substitution. However, if I use direct substitution, that would lead to division by 0. So we have to rely on other methods, and those other methods are going to have us simplify the numerator. So let's go ahead and do that. I have the limit as h approaches 0 of 1/4. I'm going to go ahead and expand out 2 plus h squared. If I do that, you could either FOIL or use the box method. Here I have 2 plus h, 2 plus h, so that's going to be 4, 2h, 2h, h squared. So it's going to be 4 plus 4h plus h squared plus 1 minus 2 all over h. From here, I am going to distribute in the 1/4 into all of these terms. And then I'm also going to simplify 1 minus 2. So let's see, that's going to give us 1 plus h plus 1/4 h squared minus 1 all over h. And then this 1 and this minus 1 will sum to 0. Notice now that every term remaining in the numerator has an h in it, so I can factor out h outside of my numerator. That would leave me with 1 plus 1/4 h over h. Now that I have gotten rid of the h in the denominator, I can now rely on direct substitution. So we have 1 plus 1/4 times 0, and that is going to simplify to be 1. So 1 is the slope of our tangent line, and something that I want to emphasize is that clearly I did not draw my graph here too well, but before we could visualize the slope of the secant line because I had 2 ordered pairs, but my tangent line, I know it only touches my graph at 2, 2, but it's also kind of hard to tell what other ordered pair that tangent line will go through. So all of that is to say, we can't really visualize and find the exact value of the slope of the tangent line that way. But at the very minimum, we should be able to recognize that the slope of our tangent line should be a positive number, which we did find to be 1 here. So 1 seems reasonable, and it's also not too far off from the slope of the secant line that we found, which was 1.5 or 3/2. So let's move on to part E, which says find the instantaneous rate of change of f for any value of x. So essentially, part E is asking us to find the instantaneous rate of change at any value on the graph of our function. So I'm just going to pick some arbitrary location right here, and the x value we can see is not even an integer. It's maybe, some number between 2 and 3, but I don't even want to approximate that because I want to just kind of generalize and say that let's say this point has the coordinates x, comma, f of x, and then I'm going to choose some other point here, and if I want this distance to be h units, then this will have the coordinates x plus h, comma, f of x plus h. And now I'm generalizing this because before we had some a value, but now what I'm doing is I'm just calling this x and x plus h. So if I use that same definition from before, but instead of a, I'm going to use x and x plus h, that should give me a function that will allow me to find the slope of the tangent line or the instantaneous rate of change for any value of x, not just limited to x equaling 2. So what would that look like? All right, so we're at E here, and we want to find the slope of the tangent line in general. And so again, we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. And just like before, we're going to evaluate f of x plus h, and so I'm going to take that and plug it into my original function. So we have the limit as h approaches 0 of 1/4 x plus h quantity squared plus 1. So if I'm highlighting here, f of x plus h is 1/4 x plus h quantity squared plus 1. And then I want to subtract off the original function. And one thing that calculus students will often mess up algebraically is we have to put minus, and we're subtracting off the entire original function. So we're going to need to use brackets or parentheses. And we have 1/4 x squared plus 1. And this is all over h. All right, let's go about simplifying this. So we have equals the limit as h approaches 0. I want to expand x plus h squared. Again, you can either FOIL or use the box method, whatever your heart desires. And then I have plus 1 minus 1/4 x squared. I'm distributing the negative sign, so that's going to leave us with that. And now what I can do is I can distribute the 1/4 inside of the parentheses. So just like in pre-calculus, when you were simplifying the difference quotient, our goal here is to simplify the numerator so that every single term has an h in it, so we can have that be factored out and then divide with the h in the denominator. Let's see if that happens. So I have a plus 1 and a minus 1. Those will sum to 0. And then I have minus 1/4 x squared and plus 1/4 x squared. So notice the remaining terms do all have an h in them. All right, so at this stage now we can factor out an h outside of our numerator. If we do that, we would be left with 1/2 x plus 1/4 h. And then we still have h in the denominator. I can now cancel out these h's. And at this point, I can use direct substitution. Now, what you are going to notice is that our limit ends up having a variable in it, and that's okay because our limit should represent a function since it's the slope of our tangent line at any value of x. So notice that if I were to use direct substitution, I would have, 1/2 x plus 1/4 times 0, which simplifies to be 1/2 x. So again, this is a function instead of just a numerical value because now I can find it at any x value that represents the slope of the tangent line at any value of x. So let's see if that function works with what we found previously. Let's go back up here, and that function, if I were to plug in x equals 2, it should match with the answer we got in part D. So here's x equals 2. If I plug in x equals 2 into this function, then that equals 1, which was the slope of the tangent line that we found in part D, as in dog. And let's do another one. Let's say we plugged in 3. So if we plugged in x equals 3, then that would give us a slope of 3/2 or 1.5, which that seems like a reasonable number. Let me do some erasing here. So x equals 3 is right there. If I drew the tangent line, it would look something like that. And the slope of that line looks like it could definitely be 1.5. It would have a positive slope. So that is the function. And so the slope of our tangent line here at any value of x is equal to 1/2 times whatever the x value is at our point of interest. So that concludes this example. Example 2 says consider the function f of x equals 2x cubed minus 5x. Find the following. In part A, we are asked to find the instantaneous rate of change, which sometimes I will abbreviate to IROC, of the function f at x equals 2. So if we were using the definitions that we had earlier, we are going to essentially find the slope of the tangent line at x equals 2, so that would be the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. So this time we have a different function, so I'm going to go ahead and evaluate f of 2 plus h. That's going to be 2 times 2 plus h quantity cubed minus 5 times 2 plus h. So that is this expression here. Now we need to subtract off f of 2. So I have minus. I'm just going to go ahead and plug in 2 into my function. So that's going to be 2 times 2 cubed minus 5 times 2. And then this is all over h. Let's go ahead and simplify our numerator now. I need to cube 2 plus h. Again, you could use the box method, you could FOIL, you could also use Pascal's triangle if you know that method. Now I'm going to distribute the negative 5 into those parentheses. So we would have minus 10 minus 5h. And now I want to simplify whatever is in our brackets. 2 cubed is 8. 8 times 2 is 16. And we have 16 minus 10 over h. Now we can distribute the 2 into our parentheses here. I think I'm going to run out of space, so why don't I move down here? Let's see, we have 2h cubed plus 12h squared plus 24h plus 16 minus 10 minus 5h. And then if we simplified 16 minus 10, that should be minus 6. All over h. So notice that in terms of the constants, we have 16, minus 10, and negative 6. And so if we combine all of those constants together, that results in a sum of 0, which is what we wanted, because now every single term has an h in it. So I'm going to factor out h from the numerator, and that leaves me with 2h squared plus 12h. These are like terms, so I have a 24h and a minus 5h. If I combine those, that would be 19h, and so I think that could just leave me with 19 there. And then we have h here. These h's in the numerator and denominator will divide out, and at this stage I can use direct substitution. And let's see, only our constant term is going to remain because the first two terms will end up becoming 0. And so our final answer is 19. So the instantaneous rate of change of our function at x equals 2 is 19. Once again, similarly in part B, we want to find the instantaneous rate of change of f at any point p with coordinates t comma f of t. So let's do that. It's very similar to the last part of the previous example. All right, so we're in part B. I'd like to find the instantaneous rate of change, which is also the slope of the tangent line. And that is equal to the limit as h approaches 0 of f of t plus h minus f of t over h. And the reason that I'm using t is because up here we're defining our fixed point to be t comma f of t. So we're just using a slightly different variable. Now I'm going to go ahead and plug these into our function. If I plugged in t plus h into f of x, that would give us 2 times t plus h cubed minus 5 times t plus h. And then, so that represents f of t plus h. Now I would like to subtract off f of t, which is essentially f of x, but now we're just replacing the inputs with t. So we have 2t cubed minus 5t, and this is all over h. And so f of t is this thing inside of the brackets here. All right, so I went ahead and skipped a little bit, but I expanded t plus h quantity cubed using Pascal's triangle. Again, you can use whatever method you'd like. I'm going to distribute in the minus 5 now. And I'm also going to distribute in the negative sign into my brackets. And this is all over h. Now I'm going to go ahead and do a little bit of simplification. Notice I have a minus 5t and a plus 5t here. And then I want to distribute in this 2. So we have the limit as h approaches 0 of 2t cubed plus 6t squared h. Now, before I continue, I just wanted to make a public service announcement. When you have the variable t, I highly recommend that you write your t with a tail and then your plus sign like that, because otherwise sometimes you're going to run into the issue of confusing your t's and your plus sign. Now, normally when I'm writing just, if I'm writing out a note or a letter, I don't typically write my t's like this. I would write it, something like that. But that in math, that looks too much like a plus sign. So that's just a pro tip. I would suggest you write your t's with a tail so you don't confuse yourself, or me if I'm reading your homework. All right, so hopefully things cancel out in the numerator in a way that we're only left with terms that have an h. So I have 2t cubed and minus 2t cubed, and it does look like everything else has an h that remains in the term, so we can factor out an h in the numerator. And now these h's will divide out, and I can use direct substitution. Let's see. So I'd have 6t squared plus 6t times 0 plus 2 times 0 squared minus 5. And if we simplify that, that should simplify to 6t squared minus 5. So once again, this is a function of t, and this tells us the instantaneous rate of change or the slope of the tangent line. When x equals t. And what's nice is I could really replace t with any value. I could plug it with 1 or 100, and it should tell me the slope of the tangent line or the instantaneous rate of change. So the part B answer, final answer, was 6t squared minus 5. And now part C says, find the slope of the tangent line at the following points. What's really nice is now we have this function, and we could very simply find the slopes of the tangent lines at these three ordered pairs by plugging in the x coordinate into this function here. So let's go ahead and do that. So we have part C, and the first ordered pair we were looking at was -1, 3. And so why don't I move this? So that I can write something like the slope of the tangent line at -1, 3 is, maybe off to the side here, I will do 6 times -1 quantity squared minus 5. So that would be 6 minus 5, which is equal to 1, so is 1. The next ordered pair we wanted to find the slope of the tangent line was 0, 0, so 6 times 0 squared minus 5, that's going to end up being -5. And then the last ordered pair that we were interested in was 2, 6. So I'm going to plug in 2 into my little function here. 2 squared is 4, 6 times 4 is 24, minus 5 is equal to 19. So those, really quickly, now that we had that function, 6t squared minus 5, we were able to find the slopes of the tangent lines at these ordered pairs fairly quickly. And then part D just wanted us to find the equation of the tangent line at -1, 3. We already found the slope, so we should be able to do that fairly quickly. We'll have y minus y1 equals m times x minus x1, and then our y value is 3, our slope is 1, and I'm going to have x minus -1. That will change and simplify into x plus 1. It doesn't tell us what form. Oh, no, just kidding. It does tell us. State your answer in point-slope form and slope-intercept form. So this would be point-slope form. And then if I isolate y, that would get me y equals x plus 4. And that would be slope-intercept form. And that concludes this example. Let's formally define what a derivative is. The derivative of f of x at x equals a is the slope of the tangent line, or the instantaneous rate of change of f at x equals a. These are some notations that you can use to denote the derivative at some x value a. So the way that we read this one here is this is read as f prime of a. So this little thing that looks like an apostrophe is called a prime, or prime notation. So f prime of a, the way that we would read this one would be y prime of a. And then, let's see, this one is not a very common notation with the capital D. I wanted to include it because it's in our textbook, but it's not one that's super common. So I'm probably going to say that we're not really going to use that one, but this other one, we would read this as dy dx evaluated at x equals a. And this one is a common notation. So these three here, f prime of a, y prime of a, and dy dx evaluated at x equals a are all derivative notations that we will be using moving forward. Note that the derivative of f of x is a function itself and is denoted by f prime of x. The input x equals a is a value from the domain of f of x, and the output f prime of a is the slope of the tangent line to the curve f of x at x equals a. Example 3 says, find g prime of 0 when g of x is equal to this rational function here, 2x over x plus 1 squared. All right, so I'm going to use the definition that we had earlier. So g prime of 0 is equal to the limit as h approaches 0 of g of 0 plus h minus g of 0 all over h. Now, 0 plus h is equal to h, and so this can actually be rewritten as the limit as h approaches 0 of g of h minus g of 0 over h. So let's simplify that now. G of h is going to be 2h over, I'm constantly reminding my students about this, and yet I also forgot. I forgot the limit symbol. All right, g of h, so that's going to be 2h over h plus 1 quantity squared minus, now I want to plug in 0 into my g function. So 2 times 0 in the numerator, and the denominator will be 1. So that's going to simplify to 0. And then I have my denominator of h. So when I subtract 0, that's just going to disappear. And I will have 2h over h plus 1 quantity squared all over h. Now this thing is a complex fraction, and h is the same thing as h over 1. What I'm going to do now is I'm going to simplify this complex fraction by multiplying by the reciprocal. And notice that I have an h in the numerator and an h in the denominator. And when I simplify that, that leads me to being able to use direct substitution. In the numerator, I would have 2 times 1, which is just 2. And then in the denominator, I would replace h with 0. So I'd have 0 plus 1 squared. That is going to be 2 over 1. In other words, that simplifies to be just 2. So all of that was to say g prime of 0 is equal to 2. And remember, g prime of 0 tells us the slope of the tangent line of the function g of x when x is equal to 0. All right, example 4 wants us to look at this rational function and find the derivative at x equals a. And so here we're not given a number, and so we're kind of more just generalizing this for any a value. So let's do that. Dy dx evaluated at x equals a is equal to the limit as h approaches 0 of y of a plus h minus y of a all over h. So if we plug in a plus h into our function, it's going to be this not pretty looking fraction, a plus h plus 1 over a plus h plus 3. So here is y of a plus h, that's this fraction here. Now I want to subtract off y of a, so that's going to be a plus 1 over a plus 3. And so y of a is this fraction here. And then this will be all over h. So how do we deal with this? I cannot use direct substitution because that would lead to division by 0. So I need to find a common denominator. Let's move this over a little bit. So my second fraction here, I'm going to need to multiply by a plus h plus 3 over a plus h plus 3. As long as I'm multiplying by some form of 1, that's okay. And then the first fraction, I would need to multiply by a plus 3 over a plus 3. All right, I have to do a lot of multiplication now, and I would recommend that you leave the denominator factored out. So do not multiply out the denominator. So in the first fraction, I'm just going to leave it as a plus 3 times a plus h plus 3. And then in the second fraction, same thing, I'm going to leave it as a plus 3 times a plus h plus 3. All right, so let's go here, and I need to multiply a plus 3 times a plus h plus 1, and I'm going to do that by using the box method. So I have a plus 3, and then a plus h plus 1. I can multiply in these corresponding boxes. I don't think there are any like terms. No, I take that back. So a and 3a, that will add up to 4a. So a squared plus ah plus 3h plus 4a, and then plus 3. Now, in the second fraction, I need to multiply a plus 1 times this polynomial here. So I have a plus 1. Here I have a plus h plus 3. And again, we have those same like terms. So we have a squared plus ah plus h plus 4a plus 3, and this is all over h. If you need to, take a minute and absorb that, rewind it if you have to. Let's move on. So now that the two fractions in our numerator have a common denominator, I can combine this into a single fraction. So in my denominator, I'm going to have a plus 3 times a plus h plus 3, and then just going to rewrite out all of these terms. That's a plus there. And then because I'm subtracting this fraction and the numerator, I'm subtracting off the entire numerator, I need to distribute this negative sign to each of these terms. And if you don't do this, your simplification is not going to go correctly. So please be careful. All right, let's see if we can't find any like terms. So I have a squared minus a squared, ah minus ah. I have a negative 3 and a positive 3, a negative 4a and a positive 4a. So it looks like the only things we're left with are 3h and minus h. And I can simplify that. Also, let's not forget about this h in the denominator. So 3h minus h is 2h over a plus 3. times a plus h plus 3, and h over 1, again, this is a complex fraction, so I'm going to multiply by the reciprocal. And look at that. This h and this h will divide out. Notice that we have no more issues if we were to use direct substitution. And so now I'm going to use direct substitution, and remember I told you not to multiply out the denominator. Notice that if we use direct substitution, this h would become 0, and we'll have a repeat term in the denominator. So that's going to be a plus 3 times a plus 3, which is the same thing as a plus 3 quantity squared. And then my numerator, 2 times 1 is 2. So here is our final answer for this example. Just as a quick reminder, this is representing dy dx evaluated at x equals a, which is another way of saying the slope of the tangent line or the instantaneous rate of change when x equals a. That's all I have for this video. Thanks so much for watching, and we'll see you next time.